Okay, so now we're going to look at how to multiply vectors. So we've got different types of multiplication. We've already done scalar multiplication. We got scalar multiplication, which I'm not going to review. We've done a bunch of that. And now there's two types of vector multiplication. We've got something called a dot product, which we would write something like this, v dot vector u. Then there's another thing called a cross product. Oh, that's not a K. It's not a product. And that's a pen. There we go. The cross product would be v cross u. So there's two types of vector multiplication where we multiply a vector times a vector. This video is going to focus on this dot product. So let's say we've got a vector 3, 4, and we want to multiply it or do the dot product with the vector 6, 8. So the way we would do this is we would do 3 times 6 and 4 times 8. So just sort of like we do the addition as well. Okay, but it has a weird meaning. So, oh, I'm sorry. We don't do it as vectors. I'm sorry. It's not a vector. It's 3 times 6 plus 4 times 8. So you're multiplying the x components, then you're adding to them, multiplying the y components. And it's not a vector. The answer comes out to be just a number. So in this case, we get 18 plus 32, which is 50. So the interesting thing here is when we do a dot product, we're taking two vectors and we're multiplying them, and we end up with a scalar for an answer. So that's an interesting kind of like what's happening here. You multiply two vectors and you end up with a scalar. You don't get a vector at all. Let's draw these vectors and see what's going on here. So if I have the vector 3, 4, I'll try to draw them to scale. If I go over 3 and up 4, that is this vector here. And then if I draw, I'm going to kind of draw on top of it in a different color. I'm going to draw the vector 6, it's like double 3, and then 8, which is like double 4. And we get this vector. All right? And the answer of multiplying those together was 50. So let's go back and look at what might be happening here. So what's the magnitude of this vector? Well, I can do Pythagorean theorem with 3 and 4, or you could recognize it as a triple. That magnitude would be 5. The magnitude of this 6, 8, if we did the Pythagorean theorem on that, we would get 10 for the magnitude. So remember, we're doing multiplication here, so it looks like if we just multiply the magnitudes of these, we get the product 50. And that's the case because these vectors are going in the same direction. Right? They're both going in that direction. So it seems like we're going to kind of call this directional multiplication. Okay? It's multiplying in a direction. So since these vectors go in the same direction, I just basically multiply their magnitudes, how long they are. The green one had a magnitude of 5. This pink one had a magnitude of 10. And so if we multiply the 10 and the 5, it seems we're getting our dot product here. Okay? Let's look at another. Let's see what happens when we have. I'm going to use two different vectors now. Let's do another example. -3, -4, dot product with 6 and 8. So again, we go -3 times 6. I'm getting a -18 plus a -32. So I'll get a -50 for our dot product. And let's see what that might mean geometrically. If I draw my two vectors, 6, 8, I'm just going to draw them both in pink at this point. 6, 8 is twice as long as -3, 4, but now they're going in opposite directions. So I end up getting this -50. So it seems that I just multiply the magnitudes, and if they're going in the same direction, I get a positive, and if the vectors are going in opposite directions, I get a negative. We're going to take a second, and we're going to look at Desmos. I have kind of something that we made here that can show you the dot product and show you what's going on here. All right, so we're going to take a look at this thing that helps us visualize our dot product. So I've got two vectors here, the purple vector and the blue vector. For right now, actually I'm going to turn off that dotted line. It doesn't have meaning for us right now. Okay, so I can move these vectors around, change their angle. So if I make them, oh, by the way, this magnitude, if I hold it up here, we can see the magnitude of the purple looks to be 2. The magnitude of the blue looks to be 1. So if I make them go in the same direction, their dot product should be 2 times 1. It should be 2 because their magnitudes are 2 and 1. Notice this dot on the x-axis, this green dot at 2. That's our dot product, okay? Now if I move one of the vectors so that it goes in the opposite direction, you see that dot moving? That's just showing me what the dot product is. If I go in the complete opposite direction, we get a dot product of, we multiply their magnitudes, but we get the negative dot product, okay? So it seems like as I move these vectors around, the dot product just bounces back and forth between 2 and negative 2 because their magnitudes are 2 and 1. So 2 times 1 is 2, right? So what happens? How do we get these other dot products when I'm moving this vector around? Well, if the biggest dot product is when they're going in the same direction, you multiply the magnitudes, and the smallest dot product is when they're opposite of each other. What would be right in the middle? It seems like 0, right? The dot product 0 would be right in the middle. What would you say about these vectors? What would be the angle between them? Right? What would be the angle between them? It looks to be that they would make a right angle. So when vectors are perpendicular to each other, then we know their dot product has to be 0. So just playing around with this dot product, right? This is what we see happens. Let's try to formalize this. So I guess it's kicking me out of where I was. So if I come back here, I've kind of showed you the same picture again. This time it has the dashed line on it, which we'll try to ignore. We notice that when the vectors go in the same direction, our dot product, if I call these vectors v and u, the dot product equals 2. We also notice that if I multiply the magnitudes of these guys, I get the answer of 2. All right, so if they go in the same direction, the dot product is 2. And basically, I'll just look at it like this. We multiply their magnitudes. If they go in opposite directions like this, the dot product would be negative 2. And the way we could get that is we could just multiply their magnitudes together and get 2. But then it's the negative of those because the vectors are going in the opposite direction. So we said, what do you think would be a dot product of 0? Like what would be right in the middle of 2 and negative 2? That would be 0. So a dot product of 0 would be when the angle is 90. And we don't multiply the magnitude. Like, well, we'll talk about what happens when we multiply the magnitude. So let's just start with this idea, actually. Let's start with the biggest the magnitude. The biggest the dot product can be is the magnitude of 2. The smallest the dot product can be is negative 2. We saw that when I pulled it back and forth, this dot, which represents our dot product, was just oscillating back and forth between negative 2 and positive 2. So it's going to be some number in between there. It just kind of goes back and forth. So we're thinking if I can take the magnitude, multiply them together, if I can multiply by some function that would switch back and forth between negative 1 and 1, that would give us our dot product, right? If I could have some function here that I multiply that oscillates between negative 1 and 1. When this function's 1, if I multiply it by that, I know that I'll get the biggest possible u times v. I'll get 2. And when this inside here is negative 1, I'll get the smallest one. And then I'll get everything in between. If the number is like, if this number inside here is 1/2 for this function, if I multiply the magnitudes and then multiply by 1/2, I'll get a dot product somewhere in between these two. Okay? So what function could oscillate between negative 1 and 1? It could be cosine of theta or sine of theta. There's a reason we choose cosine. We want when the we want the cosine of when they face in the same direction. We want the cosine of that to be equal to positive 1. I'm sorry, we want the value of that to be positive 1. And when they're in opposite directions, we want the value of that to be negative 1. So how can we tell if vectors are in what direction they're going in? We could talk about the angle between them. So if these vectors are going in the same direction, the theta between them is 0 degrees. If they're in opposite directions, the angle between them is 180 degrees. So we know that the cosine of 0 equals 1, and the cosine of 180 degrees equals negative 1. So that's why it's cosine. So this is going to be our dot product. If I keep writing v first. If I do u dot v, I am going to get this alternate formula for finding our dot product, where theta is the angle between the vectors. Okay? And these are the magnitudes of the vectors, the u and the v. So magnitude of u times magnitude of v. So what we're really essentially doing is, since we're doing multiplication here, we're multiplying the magnitudes, but then we have to adjust for what direction the vectors are going. If they're going in the same direction, we'll have our biggest possible product, and if they're going in opposite directions, we'll have our smallest possible product. Let's go back to this idea here. So now if I show you that dotted line, where was it? It was this one. Oops. I just changed the size of my vector. R is 2. Where's my P? P is 3.4. We wanted that to be 1. Okay. So it's called directional multiplication. I multiply both vectors' magnitudes together when they're going in the same direction. I multiply them together when they're going in opposite directions, but I make it negative. So what happens if they're not going in opposite directions? So let's say they're just going in different directions. I want to multiply their magnitudes together, but I want to multiply them together so that they're both going in the purple direction. So I don't use the full magnitude of the blue vector. I use just the component of the blue vector that's going in the purple direction. So you can see that's what that orange dotted line helps us figure out. We just want to use the blue part of the vector that goes in the purple direction. So when I want to dot product these two guys, and I think of it as directional multiplication, I can't just, if this is v and this is u, I can't just do v, the magnitude of v times the magnitude of u, because v is not going in the same direction as u. I'm just going to use the part of v that's going in the direction of u. So I just can use this. I'm going to use that part of v, and maybe I should do it in blue so it matches the vector colors. I'm going to take the part of v that's going in the u direction and multiply that by u. So the way that I'm not going to use the full v, I'm going to use the cosine of the angle between them of v. So that times, that times my u. That blue part times my u, that's going to be the dot product, because the blue, this part right here represents the blue part, just the part of the vector, the component of the blue vector that's going in the u direction. So I'm going to say that's vector v in u's direction. That's what that blue thing means. Okay? So if I think of it that way, I could rearrange this multiplication. Just again, think of it as u, the magnitude of u times the magnitude, I'm writing it all in one color now, magnitude of v times the cosine of the angle between them. It's the same formula. So that's another way to find the dot product. We can do it this way, or we can do component 1 times component 2 of the x's plus the y component times those vectors, right? So these are the two ways that we're going to find the dot product. And we're going to talk more about this in class. I'm going to kind of go through this again, answer some questions. I just wanted to give you a little introduction here before we jump into it.